Gate delays. We have seen gate-level modeling in our previous tutorial, and as we discussed earlier, circuits will have some delays. So, in this lesson, we'll discuss delays in gate-level modeling. Delays in gate-level modeling are called gate delays. Now, let's discuss gate delays, shall we? Gate delays allow the Verilog user to specify delays through the logic circuits. Pin-to-pin delays can also be specified in Verilog. They are discussed in our upcoming chapters. Let's start a discussion about gate delays with rise, fall, and turn-off delays. These are the three types of delays from the inputs to the output of a primitive gate. Let's discuss these one by one, shall we? We'll start off with rise delay. The rise delay is associated with a gate output transition to a 1 from another value. Here is the waveform that shows the rise delay. Now, we may get the output 0, x, or z, but due to the rise delay, we get the output as 1. Here, T-rise is the delay associated with the output transition. Next delay is the fall delay. The fall delay is associated with the gate output transition to a 0 from another value. Here is the waveform that shows the fall delay. We may get the output 1, x, or z, but due to the fall delay, we get the output as 0. Here, T-fall is the delay associated with the output transition. The next delay is the turn-off delay. The turn-off delay is associated with a gate output transition to the higher impedance value z from another value. If the value changes to x, the minimum of the three delays is considered. Here, three types of delay specifications are allowed. They are: if one delay value is specified, then this value is used for all transitions. If two delays are specified, they refer to the rise and fall delay values. The turn-off delay is the minimum of the two delays. If all three delays are specified, they refer to rise, fall, and turn-off delay values. If no delays are specified, well, the default value is 0. Here are the examples of delay specification. Now let's take AND gate as an example. At first, we shall use only one delay. As I told you, if we give one delay, the value is used for all transitions. Here we used only one delay. Delay is always specified along with a hash symbol. Let's specify this delay time as 5. So now all transitions will be delayed by 5 seconds, or milliseconds, depending on our design. Here is the waveform that shows the delay for all the transitions. That is, whenever we change the input, the output transition changes after a 5-second delay. Next, we shall use two delays. Now, these two delays will be rise and fall delays. This is how we use two delays. Let's specify the values for these delays as 4, 6. So, now during the rise of transition, there'll be a delay of 4 seconds. Similarly, during the fall time, you're right, there'll be a delay of 6 seconds. Now we shall use all the three delays in buff if 0 gate. The declaration looks like this. Here we have all three delays. Let's specify the delays as 3, 4, and 5. So, during the rise of transition, there'll be a delay of 3 seconds. During the fall time, the delay is about 4. And during the turn-off, delay is 5. Verilog provides an additional level of control for each type of delay mentioned earlier. For each type of delay that are rise, fall, and turn-off, we can specify three values that are min, tip, and max. We can choose any one value at the start of the simulation. We can use these min or tip or max values to model devices whose delays vary within a minimum and maximum range because of the IC fabrication process variations. Now let's see what these min, tip, and max variations are about. The min value is the minimum delay value that the designer expects the gate to have. The tip value is the typical delay value that the designer expects the gate to have. The max value, well, that's the maximum delay value that the designer expects the gate to have. Min, tip, or max values can be chosen at Verilog runtime. The method of choosing a min or tip or max value may vary for different simulators or operating systems. Right then, I hope you've got a better idea about this gate-level modeling, which includes gate types and gate delays. Next we shove on and go to the tutorial which deals with the other types of modeling.